Hi, welcome to the first lesson on Chapter 10 of Numerical Methods. The objectives for numerical methods is for you to be able to locate roots of f of x equals 0. So in other words, where a graph crosses the x-axis by considering changes of sign. To be able to use an iteration procedure to find an approximation to a root, or to be able to use the Newton-Raphson procedure to locate the root. And then we're going to be looking at a range of problems in and out of context using numerical methods. So what really is it all about? It's all about really the unsolvable. So over the years, you've learned lots and lots of different techniques to be able to solve lots and lots of different types of equation. And you've acquired lots of skills in order to approach them algebraically. However, the issue is that some equations are really difficult to solve algebraically, or sometimes completely impossible to solve exactly using normal algebraic approaches. So this is where the two methods, the iteration method and the Newton-Raphson method, come in. So what I would like you to do, so you understand this a bit more, is here there are 4 algebraic equations. So I'd like you to just pause the video and then just for 5 minutes use your skills to solve each of those algebraic equations. Okay, so hopefully you found something interesting in that they all ended up resulting in the same quadratic, and therefore they ended up resulting in the same 2 values of x, which were 2 and 4. So the first one, you will have had to square both sides and then rearrange it to get your quadratic. The second one, you will have had to multiply everything by x and then rearrange to get your quadratic, and so on. Okay, but you've used your skills in rearranging to be able to solve that. Okay, so ultimately you ended up working out where that quadratic crossed the x-axis. Now what you were actually doing was trying to work out where 2 separate graphs crossed. So here is the graphs for the first question. So the red line is representing the line y equals x, and the curve is y equals root 6x minus 8. So where x equals root 6x minus 8 is technically where those 2 graphs are intersecting, and you can see they're intersecting at 2 and at 4. Here, the blue curve is the graph of y equals x plus 8 over x, and the red line is y equals 6. So you, by solving that quadratic, have actually worked out where those 2 graphs intersect, which is 2 and 4. And the same for the other ones. There's the graph of y equals x squared plus 8 over 6. That's the blue curve. And the red line is y equals x. And they meet at the points 2 and 4. And the same with the last one. So by rearranging them all and figuring out where that resulting quadratic crosses the x-axis, you've actually solved points of intersection for pairs of different graphs. So that's going to be the idea. The idea is if we take an equation and we can rearrange it so it's in the form of f of x equals 0, if we can figure out where that graph is crossing the x-axis, then we can, in effect, then solve that equation. And the processes that we're going to learn are ways in which we can do that without using normal algebraic conventions. So here's just another example. So here we've got a cubic. So x cubed plus 1 equals 4x. So graphically, that green curve is the graph of y equals x cubed plus 1. The black line is y equals 4x. So you can see that there are points of intersection here, which is somewhere between 1 and 2. There's another one here, which is somewhere between 0 and 1, and I suspect there's probably another one down here somewhere. Okay, now if we can rearrange this into this and solve where the cubic equals 0, then we'll find those points of intersection. So here is that graph of y equals x cubed minus 4x plus 1, and you can see there's a point of intersection here between 1 and 2, so that's that one. There's another one here between 0 and 1, so that's that one. And then there's another one here, roughly at minus 2, so that would be the one down here. Okay, now that particular cubic, we wouldn't be able to solve using normal conventions. We won't be able to find a factor because where it's crossing the x-axis are funny numbers. But your calculator could do that for you very nicely. Okay, what we're going to be doing is trying to solve equations equal to 0, but that are hard to solve algebraically or with a calculator. The first part of the issue, or the first part of the problem, is locating where a root is roughly. So what you're going to be expected to do is show that a root is in a particular given interval. So if I just draw, I'm just going to draw a random graph of y equals f of x. So I'll just draw some random cubic. That'll do. So let's say that's at minus 4, that's at minus 2, and that's at 2. Okay. Now what I'm going to do is consider, first of all, these points here. So here, here, and here. That is where y equals 0, as you know. So those are the roots of f of x equals 0. Now, what I want to look at is the signs of the y coordinates either side of the root. So if I consider the root at minus 4, y values just to the left of minus 4, where x is smaller than minus 4, the y values down here are positive. Just to the right of minus 4, where x is slightly bigger than minus 4, the y values are positive. At x equals minus 2, just to the left of that, the y values are positive. And just to the right of that, so where x values are bigger than minus 2, the y value is negative. At x equals 2, to the left of that, the y value is negative. And to the right of that, the y value is positive. So the roots are where y equals 0. Either side of the root, there is a sign change. Okay, so it says here, to show that there's a root in the interval AB, so that's not a coordinate, that AB, that is 2 x values. We calculate f of A and f of B and show there's a sign change. So for example, I know there's a root at 2. Let's say I didn't know that, but I wanted to show that there was a root in the interval 1, 3. Then I could sub 1 into my function, and I would get a negative value. And I would sub 3 into my function, and I would get a positive value. And because there is a sign change, then that would tell me that there is a root somewhere between 1 and 2. Okay? Potentially could be more than one root, but there will be at least one root. Okay, so remember, we're going to be in a situation where we don't know what the roots are, and we have got to try and figure them out. Okay, so part 1 of the process is to locate roughly where they are. Okay, so it says, if a function f of x is continuous on the interval AB, so meaning that it's not like a reciprocal graph where it stops, and f of A and f of B have opposite signs, other words, there's a sign change, then f of x has at least one root in that interval. Okay, so I'm going to give you an example of what you might have to do. So it says for each function, show that there is a root in the given range. So for the first one, so remember to show that there's a root, we need to write it in the form f of x equals 0. Okay, so what I'm going to do is I'm going to rearrange that first equation so that it's equal to 0. So I'm just going to take root x off both sides. I could move the 1 and the minus x cubed the other side, it wouldn't make any difference. Okay, if I take root x off, then I will have 1 minus x cubed minus root x equals 0. Okay, so I've now got, this is my f of x, so I've now got f of x equals 1 minus x cubed minus root x. Now it's saying, show that there's a root in the given range. So I want to show that there's a root in the interval 0, 1. So I'm going to do f of 0 first. If I do f of 0, I will get 1 minus 0 minus 0, which is 1. Now if I do f of 1, I will get 1 minus 1 minus 1, which is minus 1. So this is positive, this is negative, which means if there is a sign change, there must be a root or a solution to that equation that is in the interval 0 to 1. Okay, now because it's a show, I need a conclusion. So I'm going to write sign change. I'm going to write f of x is continuous. Remember on the previous slide, it stipulated that f of x has to be a continuous graph. And so I'm going to say, therefore, there is a root in the interval 0, 1. Okay, now everything I've written there, you have to write in the exam, word for word. So memorise that as a quote, essentially. So obviously the numbers in the interval will change, but other than that, you need to write that every single time you do something with a sign change. Okay, so normally it might be worth 3 marks, so you might get 2 marks for doing the substituting in bit, and then you will get another mark for writing your conclusion. And you've got to say there's a sign change, you've got to say f of x is continuous, and then you've got to conclude your root. Okay, so if you could pause the video and just have a go at the next 2, and then we'll have a look in a second. Okay, so the second one, if you made it, rearranged it, so I just did 4 minus x minus log x, or you could have done log x minus 4 plus x. It doesn't matter which way around you rearrange it. When you put your 2 and your 3 in, you will have got a sign change. And then the third one, if you just take the 25 off, so you're doing x cubed plus x squared minus 25 equals 0. When you put your 2 and your 3 in, you will get a sign change. Okay, so that's basically like part A of a question is often where you have to either show that there's a root in an interval or find a root in an interval. It's usually a show question though, to be fair. Okay, now there are some exceptions to this rule. Okay, it says, can you think of any graphs that have roots for which we would not get a sign change? So are there any graphs that you're familiar with where you know that there's definitely a root, so it definitely touches or crosses the x-axis, but there would not be a sign change. I can think of one. There's one. So that's the graph of y equals x squared, or some multiple of that. Okay. Anything of that variety, there is a turn, there's a root just there. To the left of that root, it's positive. To the right of that root, the y value is positive. So it doesn't work if the graph is turning on the x-axis. So that wouldn't work, but then you wouldn't be expected to solve that. A graph where you would get a sign change but doesn't have any roots. Again, I can think of one. Can you? The one I'm thinking of is that. That's y equals, could be 1 over x, for example. In the interval, minus 1 to 1, that would give a sign change. 1 is probably around about here. Minus 1 is probably around about here. So where x is 1, y is positive. Where x is minus 1, y is negative. There's a sign change. Except there isn't, because here f of x is not continuous. So that's why that was mentioned on that previous statement. Okay, so generally it works, but there are some exceptions. Okay, you just need to be familiar. They potentially, I guess, could ask about where there might be exceptions to the rule, why it wouldn't work. Okay, we also have to be careful, things to watch out for. Okay, here in the interval AB, there is a sign change, but there's also 1, 2, 3 roots. Okay, so there's a sign change. That's why, again, it said earlier, there's going to be at least 1 root. Okay, here, there's no sign change, but actually there's 2 roots. So we just have to be careful. So the interval that we choose needs to be quite small. So you would never choose, you'd be silly to choose an interval from 1 to 10, for example, because you could have loads of roots in between. So you might choose something as close as 1, 2, where it's just 1 unit out, or even smaller. Okay, just going to have a look at a couple of questions. So the graph of the function f of x equals that cubic. Says its student observes that f of 1.1 and f of 1.6 are both negative and states that f of x has no roots in the interval. So because the student is saying that they're both negative, there's been no sign change, so the student thinks there's no roots in the interval, 1.1 to 1.6. Okay, but if you look closely, that's about 1.3 there, and that's about 1.6 there-ish. Okay, there's actually 3 roots in the interval, so they've made the wrong conclusion. Okay, so that's with reference to the diagram. So it tells us to calculate f of 1.3. So if we do f of 1.3, so we're just going to substitute 1.3 into here, here, and here. So f of 1.3. And then we also have to do f of 1.5. So if I do f of 1.3, if I substitute it into here, you could use the x on your calculator and the calc function. That gives us 0.088, which is positive. If I do f of 1.5, that gives me negative 0.5, which is obviously negative. Okay, so what have we got? We know f of 1.1, the student observes, is negative. So it's negative. F of 1.3 is positive. F of 1.5 is negative. F of 1.6, the student observes, is negative. It says calculate that, explain why there are at least 3 roots in the interval. Well, how many roots have we got so far? If we look at the sign changes, there's a root here, there's a root there. So in the interval 1.1 to 1.3. There's a root here in the interval 1.3 to 1.5. But so far we've only got 2 roots. Okay, but it does say in the interval 1.1 to 1.7. So what I think we should probably do is work out f of 1.7. If we do f of 1.7, I get 0.352, which is positive. So that is our third root in the interval 1.6 to 1.7. Okay, one more question. It says, using the same axes, sketch the graphs of y equals natural log x and y equals 1 over x. Explain how your diagram shows that the function f of x equals log x minus 1 over x has only 1 root. Okay, so if I start with natural log x looks like this. Try and do it justice. Going through 1 there, and there is an asymptote, which is the y-axis. Okay, remember log x can never be negative. Oh, we can't have a log of a negative. So there is no, log does not exist for negative x values, I should say. Okay, 1 over x looks like this. So in that first quadrant and in the second quadrant. Okay, so we can see from our diagram that there is only 1 point of intersection here. Okay, but it's not enough just to say that. We need to show algebraically how those two link to that. So again, this links back to the starter. That point of intersection is where log x equals 1 over x. So that point of intersection is where y equals log x and y equals 1 over x meet. So where log x equals 1 over x. Okay, so in order to get to that point, I just need to take off 1 over x to get log x minus 1 over x equals 0. Therefore, f of x equals log x minus 1 over x. Okay, then I can say there is only 1 point of intersection. Okay, so you need to show this bit algebraically, and then you need a statement about the fact that there's only 1 point of intersection. Okay, so that was part A. Part B, show that the root lies in the interval. Okay, so we're going to start with this here, and we are going to substitute in our values in the interval. So if I do f of 1.7, so log of 1.7 minus 1 over 1.7 is negative 0.06. If I do f of 1.8, I will get positive 0.03. Okay, so we've got a sign change, so we know that that root is somewhere between 1.7 and 1.8. So we're going to make our little conclusion. we're going to say that there's a sign change. We're going to say that f of x is continuous. Now I know that graph is not continuous, but that's two separate graphs. Okay, what we're saying is that certainly in that interval, that function is continuous. Okay, so it's still valid. Therefore, root is in the interval 1.7 to 1.8. Okay, part C says, given that the root of f of x is alpha, show that alpha is 1.763 correct to 3 decimal places. So what we need to be doing is thinking about how can we show that the root that we've got is correct, is 1.763 correct to 3 decimal places. Well, it's the same process as what we've just been doing with a sign change. So we need to think about what 2 numbers can we substitute in for our interval that would show that the root must be 1.763 correct to 3 decimal places. So there's our 1.763. What number could we have here and here, which are our interval numbers, that tells us that the root must be 1.763? Okay, those 2 numbers are the bounds. So we're going to substitute 1.763.5 and 1.763.25. If we can get a sign change in that interval, then both of those numbers round to 1.763. Remember, it's a bound, so don't be thinking it's going to round to 1.764. It's an upper and lower bound for a continuous set of numbers. So if we do f of 1.7635, I get 0.0002, and f of 1.7625 is negative 0.0006. Okay, now remember, the root is where f of x is 0. These numbers here are really small because we are now really close to the root. So by being almost on the root, that's why we're getting almost 0. Okay, however, we've still got a sign change. Okay, I'm not going to go through all this bit because I know the fact that that is the root because I've been told in the question. So I'm just going to put the root alpha is 1.76323 dp's. Okay, that is the end of the first video. You should now be able to have a go at the questions on exercise 10A.